Okay, let's continue. So, basically, last time or so far, what we have done is to define what waves is, and we also talk about how to describe a wave. We will talk about that there are two types of waves: longitudinal waves, transverse wave, and then for longitudinal waves, there are some new terminologies. We call it compressions and rarefactions. Essentially, a location where you have a higher density of particles or a lower density of particles. And afterwards, we introduce ways to describe a wave, and we took transverse wave as examples. Well, there are two types of graph. The first type of graph is the displacement distance graph, and that is essentially capturing the position of all points on a wave, and from that graph we can obtain the amplitude and the wavelength. And the second graph is the displacement time graph, where we do not look at the position of all particles. Instead, we focus ourselves on the motion of one particular molecules or a particle in the wave, and we obtain a displacement time graph. The feature of displacement time graph is the same as we learned from mechanics. In particular, you can obtain the velocity from the displacement time graph by finding the gradient of the displacement time graph. However, here of course, that is part of the syllabus, that you need to know how to obtain velocity from a displacement time graph. However, here our focus is a little bit different. The difficult part is how to sketch the displacement time graph. That we know basically all displacement time graph for a wave must be this kind of sinusoidal waves, these oscillations. However, how to really sketch, then we use a trick. A very powerful trick is that you need to on top of the displacement distance graph, you need to sketch the wave at the next instant. So essentially, what we do is to shift the wave to the direction of energy transferred by a very small displacement, and then from that you can deduce that the particles motions accordingly. For example, this part is quite important, so I repeat a little bit here. First, that you have a line in black which refer to the wave at this instant, and then you also have the wave at the next instant, in which I just shift the wave to the right hand side by a bit. And then from that, therefore, initially, if you have the particle 3 located on the line in black, then at the next instant of time, the particle 3 will be found here. So therefore, it means that the particle 3 during this interval of times has moved upward. So we can conclude that number 3 is moving up, while number 5 is moving down, and number 1 is moving down. While for 2 and 4, they are special case because they are the turning point of the oscillation. So therefore, at the moment when they reach the turning point, we describe their motion as momentarily at rest. And afterwards, then we got this displacement time graph, and these displacement time graphs allows us to deduce the amplitude and period. And the amplitude we deduce from the displacement time graph, is the same as the amplitude we obtained from displacement distance graph. And well, after we get to period, then we can talk about frequency, which is just the reciprocal of the period. And the physical understanding is not difficult here. The only confusion may be you may mix up these two physical quantity. And the last time, a very useful tools I use myself is to look at the unit. The unit of frequency is in hertz, while the unit of period is in seconds. Therefore, if your final answer is in the unit of seconds, that means you have find a period, not the frequency. And then finally we get to the wave equations, and then I did not go through the proof. You can read the proof from your textbook if you are interested in. But I want to emphasize the importance of understanding the physical meaning behind these three variables. It is not just for the very first part of this topic we will need to know that. Afterwards, when we get into refraction, we also need you to know that the features of these wave speed, frequency, and the wavelength. Well, in short, we say that wave speed depends on mediums. So therefore, if you have a wave travel in another media, then you will have the speed changes. While for frequency, it will depend on the source. And my statement I always make is that if you want to change the frequency, you need to walk to the source. For example, a loudspeaker, and then to change the loudspeaker setting. Otherwise, you cannot change the frequency of the wave. Well, then finally, wavelength just depends on frequency and wave speed. And then we also learn about something called wave fronts. Wave fronts are just those lines that refer to the location where you find the peak at the wave. For example, usually on the side wheel, you have peaks located, and then if you want to represent this wave from a top view or the bird eye view, then you can I'm mixing up the fish eye views. The bird view, then you have the we will usually represent the position of the peaks by lines. They are the wavefronts. Last time I emphasized two things. I emphasized only one thing, which is the separation between adjacent wavefronts is one wavelength. This can be understood when you look at the side wheel, because this is just the distance between two peaks. And I forgot to mention one thing last time. That would be that the wavefronts will always be perpendicular to the ray. So therefore, you need to have a 90 degree here between the ray and the wavefronts. I'll give you an example later. And then afterwards, I look at this example. Okay, so today I will try to finish the foundation part of waves. That will be what we covered today. So let me give you one more example about the rays and the wave fronts first. Example about a ray is perpendicular, or let me make it very general. Rays are perpendicular to wavefronts. Well, of course, we did demonstrate last time that when you have a ray, going this way, ray just carry the direction of energy transfer, and then we have the wave fronts to be this way. So, well, this is the wave fronts. So the first feature is we say that this is in one wavelength. So wavelength. Well, one important thing is because when the wave travels, the wave fronts have to be perpendicular to the ray. This is really just an observation we find in daily life. The example you can have in your mind as a mental picture is the water waves. So when the water waves travels outward, so like this. So this is the water wave. This is the wave fronts then. Then we will have, it means that the energy is transferred radially outward. So therefore, this just leads to the observation as a quite universal observation is that you will always have 90 degrees between the ray and the wave front. And if we draw another smaller one, let's say you dropped a droplet into a pond, then you will see this kind of ripples. I think like you have ripples. And then, well, what does that mean? It means that the energy is transferred radially away from the center where you drop the stone there. And this will again be an example that you can see that the ray and the wavefronts are at 90 degrees. So this is one thing that we have to bear in mind when we try to demonstrate in the future. Yeah, we'll talk about that later. So this kind of feature seems not particularly challenging. Well, if this kind of question come along, you may not make any mistake. Well, however, it can be actually be more subtle when it comes to refractions. I do not talk about refraction now. I will save all wave phenomena at the later part. Today, or the last lesson and this lesson, we just want to discuss the foundation of waves. We do not describe any phenomena yet. But let's just put a remark here to remind ourselves that this becomes non-trivial when we talk about trivial in refractions. It turns out that when we draw the ray for refractions, the wavefronts becomes quite complicated. Another feature, just to remind yourself as well, okay. And another feature we need to remind ourselves is that the distance between adjacent wavefronts, it has a physical meaning, which is the wavelength. Well, that means if you suddenly, let's say you draw something, you draw a ray, or you're given a ray, and then for some reason they give you the wavefronts, and then suddenly the spacing between wavefronts changes. Then what does that really imply? Well, because first of all, it means, of course, the wavelength is different. So here is this longer wavelength, and here means you have shorter wavelength. This is the first immediate consequence. Well, however, we learned that the wavelength is related to wave speed and frequency, while frequency can never be changed. As I mentioned before, if you want to change the frequency, you need to walk to the source and then change it. So therefore, we must have the same frequency, because it is just a wave emitted by one source. Then by the formula that V equals to F lambda, it means that for the first half, we actually have a higher wave speed. And for the second half, it must have a lower wave speed. Well, but we learned that wave speed only depends on the medium. So therefore, it implies that the two mediums here are not the same. So this part here having a shorter wavelength, and this part here having a longer wavelength, implies that they are in two different mediums. It means that the wave travels into a new medium. So actually we did this before last time, but I want this time, the way I demonstrated is you deduce from the separation between adjacent wavefronts and conclude that the wave has entered a new medium. So in other words, if the wave does not enter a new medium, then the separation between wavefronts should remain unchanged. So, well, diagram explain everything. So you really just have the same medium all along, then wave speed should not change. So if it is same medium, that means that V is constant. Then it means that lambda is uniform, because F is constant. Then in this case, you are talking about the wave traveling in one single medium. Okay, now this is a little bit elaboration I want to add for the rays and wavefronts. So today we try to follow what we did last time, and then we talk about the description of longitudinal waves. Well, description of longitudinal wave. Well, first of all, let's make a motivation to understand why this is a bit non-trivial. Well, transverse wave. Let's recall what we did on transverse wave, or how we study transverse wave. Well, I borrowed the diagram. Transverse wave is, or let's say I have a transverse wave. Let's make the water wave as an example. A water wave is a very good example of a transverse wave. So I have a water wave. And then last time, we just learned that a water wave, if you really want to produce a displacement distance graph, it is very simple for transverse wave. Because essentially, transverse wave just look like a displacement distance graph. All you really have to do is just to take a picture and then just put it onto a displacement time graph. Let me use this color. This is what we did last. No. Let's move in another color. So something like this. No, this also looks not good. I think actually I need to make it blue first. So I have a transverse wave like this, and then it's like you just from this graph you obtain displacement distance graph. You look at the real wave, and then you obtain displacement distance graph. In this displacement distance graph, what you can get is that you can get amplitude and you get wavelength. The way we get from the real wave to a displacement time graph is trivial, easy. You just take a picture, essentially. Yeah, trivial. I like to use this term a lot. Trivial. Well, after you get the displacement distance graph, what you can achieve from that is that you can get displacement time graph. Just like what we did here. We obtain the displacement time graph from a displacement distance graph. Maybe you have noticed this last time already. That would be nice. But here I want to repeat a little bit so that you can see the structure. So after that, we obtained from this graph, then you can obtain displacement time graph for whatever particles you're interested in. So you get from a real wave to a displacement distance graph, and you get into displacement time graph. And when you get displacement time graph, you got amplitude again, as well as time period t. And then once you get t, you get frequency. Thus frequency is just f equals to 1 over t. And once you get t and f, you get wave speed. Because wave speed is just v equals to f lambda. So therefore, basically what we did for transverse wave is like this. Start with the actual wave, take a screenshot, put it onto a graph. Afterwards, based on the graph, with the skills we learned last lesson, we obtain displacement time graph to whatever particles you are interested in. And after that, you get the period t, you can calculate frequency, then you can use the wave equation. Well, this part is essential. Because for transverse wave, the shape of the wave is really just look like the displacement distance graph. However, for longitudinal wave, you have a complete different story. How does we are here? So therefore, what we find here is displacement distance graph can be easily obtained. In or for transverse wave. Well, however, when we get to longitudinal wave, it will be not the same. Well, you look at a longitudinal wave, we talked about that before in compression and rarefactions. So let me borrow this diagram. This will also be a type of diagram you will frequently see in examination. Now, for longitudinal waves, you will need to first be given, first of all, the longitudinal wave will be mainly about like you have the points, you can just mainly take them as the air molecules, the position of air molecules, and you will need to always be given two patterns of wave. This will be, the first one is the pattern of waves, the pattern of the air molecules when there is no wave at all. And then the second pattern is when there is a wave coming by and you freeze the time at a certain instant. Well, we need these two patterns because we need to compare them to find out rarefaction and compression. This is what we did last time. Now you see, the actual wave has nothing to do with the displacement distance graph directly. For the transverse, you just take a picture and then you put it into displacement distance graph. But for this one, you just have dots. This is not easy to translate these dots into a displacement distance graph. And that is what we try to describe it now. Now, how to get displacement distance graph? Well, there's a trick. First of all, we are finding displacement. So therefore, let's look at all these particles to see which particles here has zero displacement. Well, zero displacement does not mean it did not move at all. It just means that when you look at the wave, it just so happened that you find the particles at their equilibrium position. That point can be moving, can be not moving, we don't know. But its location is at its equilibrium position. Just like, for example, at the very beginning, you see your classmate standing in front of you, and then you close your eyes, and then close your eyes for 5 minutes, let's say. Your classmate may have walked away, come back, walk away, we don't know. But when you open your eyes, and then you see your classmate standing right in front of you, then he or she has zero displacement. It does not mean it is at rest for the whole 5 minutes. It's just so happened that he or she is located at the location where you first see them. So in this case, you will have 1, 4, 7, and 10, and 13. These particles, they have zero displacement. We got this by just really comparing the two patterns. Well, now, what do you see is that you see that they are all location of special point of interest like compression, rarefaction, like this. So therefore, this is the first idea that what we have, and we put it here, is that compression and rarefaction have zero displacement. Now this is something you can just convince yourself by comparing the two patterns, or you can just think about why it has to be the case. Well, for understanding, let's suppose you are at the location of compression. So let's say you are the compression. What does that mean when you say you are a compression? It means that the classmates standing next to you have a tendency to move towards you, so that you are at the center of high density of particles. Like this. Then you call your location as a compression. Well, conversely, if you are a location of rarefaction, then you will be having your classmates moving towards you. Moving away from you. Then you will be at the location of the lowest density. Now you see, people on your right hand side, they move to the left, while people on your left hand side move to the right. So therefore, they have opposite displacement. Let's suppose I say that I have positive displacement to the right. They take this as the convention. Then that means the people on your left hand side, they have positive displacement, while the people on your left hand side, they will have negative displacement. Well, by the continuity, if you have positive on one side and a negative on the other side, then you're at the middle. You do not belong to left or right. You do not belong to positive or negative displacement. Then that means you have zero displacement. On the other hand, for rarefactions, the people on the right hand side move to the right, so they have positive displacement. And those particles or people on the left hand side, they move to the left because they have to move away from you, so they have negative displacement. By continuity, you are at the center, not to the right nor to the left. Therefore, you are having zero displacement. So therefore, from this we can understand why it will be universally true that compression and rarefactions will have zero displacement. Well, that is a very important observation because it allows us to use them as the backbones of the displacement distance graph. So this is displacement distance. And these points we have 0 displacement. Oh, and then from this, you only left with 2 possibilities. Either the wave will go like this, or the wave will go like this. To determine that, we just take 1 as an example, or as a sample. 2 and 3, they have moved to the right, because 2 initially is here, and now it is here. 3 is here, now it is here. So it means that they have made a positive displacement. So they move to positive displacement, while 5 and 6 will be negative. 6 and 8 and 9 will be positive because they have moved to the right, and this is negative. Well, therefore, I should have a positive displacement, and then negative displacement, and then continue, etc. And this is how we sketch the displacement distance graph. Now, what is the kind of the lesson learned? The lesson learned is when we are given this kind of longitudinal waves, what we should do is to identify those locations where you have 0 displacement. Accidentally, they are also the region of compression and rarefactions. After that, then we can continue to plot them as the backbones on a graph. Then we are only left with 2 possibilities. One like this, and other one is the opposite of it. Then what we need to do here is to observe the graph, look at the notation of the questions. Usually is to the right as positive. Then that means these particles here, they have positive displacement, so I'll give them positive displacement on the graph. Well, a last thing we want to talk about here will be how to find a wavelength. Usually from here, it may not be that obvious to find a wavelength. However, when you are given this, it's very easy to find a wavelength. Well, the wavelength can be just from one compression to another compression, then that complete one cycle. This is one wavelength. So you can also use one rarefaction to one rarefaction for one wavelength. But at least it's not between compression and rarefaction. Between compression and rarefaction is only half a wavelength. Okay, now therefore let's make it as a remark. So we make the observation already. Compression and rarefaction have 0 displacement. And the other remark will be the distance between adjacent compression is one wavelength. So in particular is not between compression and rarefaction. So there is a types of question to ask besides the way that you can talk also about the amplitude. Then you find out, well, where do we find the amplitude? Amplitude, we usually find it here. This is amplitude. So that means I need to find out the one which displaced by the largest amount from the graph. This one, I left you to try out yourself as an exercise. It was tested in the past year question. Now, well, these will usually the backbones of your understanding of so-called general understanding or the general description of waves. And then now I will add some supplement, in my point of view, is that it does not really follow the main storyline, but somehow you still need to know it for the examination. Let's do it like this. So just some supplementary materials. These are something that you will encounter in multiple choice, not tested very frequently. Well, for example, there's no long question that they can test you. But let's also get through that. Well, you read the test over, you can get this kind of knowledge already, but I just spend some time to talk about it. Well, the first of all is we summarize it in this way. For example, we look at sun. Well, we know that sun must be a longitudinal wave. 1 second.